Video, sound.
Okay, welcome to day 28 of 28. We have made it to the end of the course. A whole bunch of administrative items. Number one, final exam is next week. At 10:30. I'll post the Zoom link, but it will be the same as today's lecture. I have posted a link to the course evaluation. So the college does not do evaluations during this time, but the department, we had the BME department do. We always, at the end of every school year, we always meet as a group, the faculty, and we discuss all the feedback that we got, and we talk about ways that we could improve certain things. This was a challenging year because of the remote learning. We did our best. I mean, I certainly did my best. I think that all in all, you guys learned as much, definitely as much as previous cohorts have learned in class. And I will just post a link to the survey now as well in the Zoom link, in the Zoom chat, just so, because I really hope that everyone does fill out the survey. It helps the department with making adjustments, etc. For future years. Just get the link. Okay. The plan is to be in person next year, if you're vaccinated. That's the current plan. And I do, like, as I was telling a student recently, the college is definitely very motivated to have everyone back in person. Okay, the important things, the important admin items are that I posted practice problems from lectures 9 and 10. They're from the back of the book. And what I'm gonna do now is I'm just gonna try to scroll through them, and because I want to focus your preparation for the final, so I'm going to try to do my best to kind of emphasize which problems you should be doing from lectures 9 and 10. So lecture 9 is really just there to get you up to speed on complex numbers and phasors. Oh, where is it now? I just had it. Okay, here we go. And so historically, the final exam has had 4 problems and a bunch of multiple choice. The multiple choice are my gift to you. You know, I don't think that anyone who has attended the course and stayed awake and who has prepared for the final exam, they should have no problem in getting most of the credit on the multiple choice. And then you will have 4 problems to solve. And one of them will be first order step response. First order step response. If you go to the back of the book and find the section that says first order step response, try to do as many of those as you can. Do the practice problems from the lecture and do them covering up the solution and try to reproduce the solution. Last part of lecture 9 is not uploaded. Give me a second. Every lecture should be there. I'm kind of surprised. Let me just check. Lecture 9. Or maybe not. Let's see. May 8th. Ah, you may be right. Okay, was there, let me just check the calendar. May 5th, May 3rd. Okay. You're right, and I apologize for that. I don't know how. I thought I uploaded all of them, but I will upload the May 10th lecture right now. What I'll do, let me just see. What I'll do now is post it on the chat just so you don't have to wait for the whole YouTube song and dance. No, I have not made a practice final. I'm actually trying to do it in Blackboard, just to avoid any, because the Blackboard, you know, for all the things that it didn't do, we didn't have any technical issues on the midterm. So if I can try to use it again for the final while still accomplishing what I needed to accomplish, I'll do that. Okay, so what I'm gonna say is, did I let everyone in? Go back to sharing my screen. Where was it? Okay. So the 4 problems for the final are going to be first order step response, second order step response, and there will generally be 2 questions from chapter 10. And the reason I like chapter 10 is because it covers everything. It covers, you know, like this nodal analysis section. It's great because not only am I testing you on nodal analysis, I'm also testing you on phasors and KCL, you know, complex, you know, inductance, capacitance. So it's a really good holistic test. So the 2 questions from chapter 10 will generally come from nodal analysis, mesh analysis, Thevenin and Norton. That's where it has been historically. There may be a change this year, but you know, like it doesn't mean that you should completely neglect source transformation and superposition. But historically, they've come from nodal analysis, mesh analysis, and Thevenin and Norton. People are still coming in. Hold on. Yeah, camera on. Yeah, the Zoom with the camera on. No, that's 100%. You need that. Oh, very important. I have not received very many of your IDs, and you cannot write the final without submitting your ID. So I think like 2/3 of you have yet to upload it. So what I will do, I'll again put it in the Zoom link. So once again, if you have not, wild echo there. If you have not uploaded your photo ID, please do so here. Sorry. Okay, so there's the link to upload your IDs. I have to cross-check everyone's Zoom video with their face on Zoom during the exam. Okay. The review of the course evaluation. I've posted practice problems from lectures 9 and 10. There will not be a homework due to time constraints, but you should practice the problems there, as well as the ones in the lecture slides before next Monday. Let's see, what else did I want to cover? Yeah, again, importantly, first order step response, second order step response, Thevenin and Norton, nodal mesh analysis from chapter 10. Chapter 9, again, it's just like a primer for complex numbers and phasors. So I'm saying all this to help you guys focus your preparation for next Monday. Okay. If you're unmuted, please mute yourself. Unless, of course, you want to ask a question. I think that's all the admin items. I do want to spend the rest of the lecture, that is until 3:15, covering as many problems from chapter 10, from lecture 10 as possible. Let me see if I can figure out who's unmuted. It's gallery, that help. Ah. I have to go through every one of these to, oh, there must be a better way of doing this. Participants.
Isn't there, I think there's a mute all button for the host, right?
Yes, I think I just found the culprit. I won't name the person, but I think I just found him. Okay.
Professor, one question.
Yes.
For the 4 questions, do we get to pick the 3 out of 4, or would you want us to answer all 4?
I have not made up my mind yet. Typically, it's been you have to do all 4, and the reason for that is we have to you need to demonstrate your knowledge of first order circuits and second order circuits. So you got to do at least one of those. So it's most likely it will be do all 4. There's an outside chance that you'll get to pick one of 2 from the chapter 10. No, but you do have to do first and second order circuits. But in the past, I've always made everyone do all the problems for the final. Okay. Let's do as many of these as we have time for. Our first problem, for me, this is about slide 26. It's a superposition problem. We are asked to find V naught. And so what is different about this problem is that we have two frequencies involved. We have a omega of 5 on the battery, and we have an omega of 10 for the current source. So the solution to this problem is to analyze the response of V naught separately for the voltage source and separately for the current source, which means we're going to draw the circuit twice. Okay, so first we're going to draw it with only the voltage source. And our omega here is equal to 5. That's important. And so now let's draw that circuit. Let me actually make myself more space. And let's see. I'm just going to put boxes for all the impedances just to. And then the current source just becomes an open circuit, so we can just ignore it. So this here, so this is a capacitance of 0.2, and the frequency is 5. So 1 over, so this is 1 over paying the price for not making this lecture auto admit. Okay, so this becomes the impedance of the capacitance becomes 1 over J 5 times 0.2, and that equals to negative J. Okay. And then the impedance of the inductor just becomes J5, and the impedance of the resistor is just 8. And so we need to write the battery as a phasor as well. And so as a phasor, this just becomes 30 angle negative 90. And so 30 angle negative 2. Because it's a sine. So a sine is equal to a cosine with a minus 90 phase shift. And we need to find the voltage across, we need to find the voltage here. Oops. Okay, and so probably the easiest way of doing this is to combine these two impedances into a single one. So we can, let's just write ZC is going to be equal to negative J in parallel with J5. And that becomes negative 1.25J. So, and the way you get that is just product of, so if you multiply these together, you get negative J squared times 5, which is 5, and you add them together, it's J4. So it's 5 over J4, which is 5 over 4 times negative J. Okay. And so now we can just use voltage division. namely that V naught is equal to 30 angle negative 90 times ZC over ZC plus 8. Okay, so hopefully, and this is just, so you're looking for the voltage across this part of the circuit, these combined branches, these are in parallel. So they have the same voltage, and that voltage is V naught, which is the thing we're interested in. And so when you, because we don't have time for me to actually carry out the complex arithmetic, I'm just gonna give you the results of the computations. I think in a couple of instances, I will actually show you the math. But the answer becomes 4.63 angle negative 171. In other words, V naught of T becomes 4.63 cos 5T minus 171. So that becomes the solution, the first component of this superposition solution. Okay, before I move on to the current source, does anybody have questions as to what I did to solve for V naught with the battery in place? All right. Jump in with questions whenever you have them. And now we're going to do only, oops.
I'm just confused about the voltage division step.
Yeah. So it's like your interest. So if you had a battery and you had resistor 1 or impedance 1 and impedance 2, right, then V, this voltage is equal to this times, like if this is V and this is R1 and this is R2, then voltage division just means that the voltage across this resistor is equal to R2 over R2 plus R1 times V. And so you're doing the exact same thing here, except that you've combined, these two are in parallel. And so they can be effectively combined into a single impedance. And you don't have to worry about the fact that you've combined these two things, because the thing that you're after is the voltage. If you're after the current, that would be different, but you're only after the voltage. Let me just take the chat question maybe. Yeah, so Christian, the answer is no, you cannot. It's a good question. I understand why you would guess that, but because voltage, the reason that you do voltage division is because of Ohm's law. So another way of solving this would be you simplify this impedance and then you add it to the 8, and that gives you the total impedance in the circuit. And then divide the voltage by that total impedance and you get a current, and you get how much current comes out of here. And then that current will will pass through this combined voltage. But both the calculation of the current and the combined voltage drop across these two is dependent on taking into account the J5. So you cannot ignore the J5, unfortunately, because the amount of current that comes out of the battery here, so the battery does sense both the capacitor and the inductor. And so you do have to consider the inductor when solving. I think we're going to get another little demonstration of voltage division, or actually current division here for the current source. So the thing to note here is that here, omega is now equal to 10. So that changes things a bit because now we have to update and this becomes a short circuit. So our circuit looks like this. And now this, the current source is just 2 angle 0. And now this impedance of the inductor is J omega L. Omega is now 10. So this impedance is now J10. And this impedance is now 1 over J omega C. Omega times C is 10 times 0.2. So this becomes negative J over 2. And this is still just equal to 8. So this is our circuit. We are interested in the voltage here, V naught. So there's a couple of different ways to approach this. Let's see. How did I do it here? Probably the, let's see, there. So I combined, right, so I combined these two. These two impedances are in parallel. Right, so I'm just going to call ZC is equal to 8 in parallel with negative J over 2. And so we can actually get this math is simple. So it becomes product over sum is negative J4 over 8 minus J2. And we can actually leave it like that. And now we are interested in the voltage here. So notice that the voltage V naught here is equivalent to the voltage here. This is also equal to V naught. And so if we get, so now what we've done, let me just clarify what I just did. So this is now ZC. And this is J10. This is my current source. And so you can to figure out what the voltage is here, you can get either one of the currents. I'm just gonna solve for this current. I'm gonna call this I naught. And then once I solve for I naught, I will multiply it by J times 10 to get the voltage V naught here. But I could have equally solved for this, the current through ZC, and then multiplied that by ZC. They will both give you equivalent answers. So I naught is equal to 2 times ZC over ZC plus J10. So this current division applying to this circuit. And what I've done, ZC is a combination of the 8 ohm resistor and the capacitor. Now we'll just tell you that I naught ends up being 0.105 angle negative 176.24 degrees, which means that V naught is equal to J10 times I naught. So it's basically this multiplied by 10 and then advanced by 90 degrees. And again, you're allowed a calculator on the exam. So if you have a calculator that does complex multiplication, by all means use it. You know, I certainly don't want, I'm testing your circuits knowledge, not your complex analysis. So V naught T here becomes 0. Or sorry, oops, that's a mistake. My bad. Try this again. V naught is equal to I naught times Z times J10, right? So we solve for this current through the J10 impedance. So using Ohm's law to get the voltage over here becomes 1.05 angle negative 86.24, which means that V naught of T is equal to 105 cos 10T minus 86.24 degrees. Okay, so that becomes the second part of the superposition. Okay. And so the final solution becomes V naught T is equal to 4.63 cos 5T minus 171 plus 1.05 cos 10T minus 86.24. Try to bring it up if I can. Let me see, to make some room here, or I'll put it at the top. Plus, so I'm basically just adding the two sub-solutions. And notice that they are occurring at different frequencies. So this is the part of the response that occurs at the 5 frequency. And this is the part of the response that occurs at the 10 frequency. Wouldn't just be easier to use current division since all are in parallel with each other? Yes, they are all in parallel with each other. Yeah, I may have gone about this in a roundabout way. I mean, at the end of the day, you need to solve for any one of the currents to this branch, or this branch, and then multiply that current by the impedance. And that, so the voltage drop across these three impedances is all equal to V naught. So however you want to do it, will give the same answer. And yes, maybe current division. So I did current division. I did it here. This is current division. I just did it after simplifying these two, but there's several different ways of getting at the answer here. All right. Let's move on to source transformation. We have one source transformation problem that we are going to tackle, and this is not a difficult problem. It's just going to be a lot of drawing for me. And so I'm going to redraw this. Basically, source transformation is, maybe I'll back up a few slides. So source transformation is swapping a battery in series with an impedance with a current source in parallel with that same impedance. And as long as the voltage source is equal to the impedance, the load times the current, and the current is equal to the voltage divided by the load, you are perfectly able to do this. So if you have let's say a 10 volt and a 10 volt battery and a 10 ohm resistor here, you can equivalently write that as a 1 amp current source and in parallel with a 10 ohm resistor. So in other words, source transformation applies equally well to AC circuits as long as you have the circuit expressed in terms of phasors. So you now are going to have a phasor for the impedance, for the current source, and you're going to have a complex number for the impedance itself. And so there are times when it's convenient to be able to switch a battery to a current source. So when you want to make a giant parallel circuit, you'll go from here to here. When you want to make a giant series circuit, you'll go from here to here. Okay, and that's what we're going to do here. We're going to do a bunch of source transformations to try to make this problem a little bit easier to work with. So as a starting point, we're just going to simplify a couple of the impedances that are in series. So this here is going to be the combination of 4 minus J3. This is going to be 2 plus J. This is going to be J5. This is going to be 1 minus J2, and I'll fill all those in now. This is 4 minus J3. This is 2 plus J. This is J5. And this is 1 minus J2. So right away, there's a couple of things that would help. Namely, we have a current source here of J4. So why do I call this J4? If you're unclear, if you have the complex plane and you have a phasor with a magnitude of 4 and an angle of 90, that's equivalent to J4 because this is the J axis. So 4 angle 90 is equivalent to J4. So this is my circuit. And now what I'm going to do is I'm going to take this and I'm going to express it as a battery. In series with 4 minus J3. I'm just going to keep these two over here. And now this is still 4 minus J3. And this is still 2 plus J. So now these two will be able to be combined in just a minute. So the question is, and this is a question for you, what is the value of the battery here that I have to put in? So the current source was J4, and it was in parallel with 4 minus J3. So what is the value of this voltage source here that I have to put in? Excellent, Christian, that's great. It is 12 plus 16J. And so the way you get that is you have to multiply 4J by 4 minus J3, right? So if you write out J text, so J4 times 4 minus J3 is equal to 12 plus J16. And that's what becomes the value of the battery. It's over here. Okay. And so now, what can we do? I did a bunch of steps here, so I'm just gonna go with what I have. Now I can do, let's see, what was my next step? I think I skipped a step. See if I can erase this. I'm gonna combine this. So this is gonna be 6 minus J2. Just take the check. Yeah, that's right. Your suggestion was good, Christian. And so let's see. And now that I have this, I can go back to a current source. So now it'll be great if they let you copy and paste this. Let me see if they let me. Oh, I think they do. No, let's try it again. No. All right. So let me just erase this again. Erase this. Kind of fill in. So it's going to be so this is again going to be 6 minus J2. And now the value of this battery is going to be equal to this, the 12 plus J16, divided by 6 minus J2. That's going to be over here. Because now I've gone from the previous step, there was a battery in series with 6 minus J2 to a current source in parallel with 6 minus J2. And this is still J5. And this is still 1 minus J2. Okay. And so now I'm working my way closer to an easy circuit. So now I'm going to go back to the current source. And I'm going to make one more simplification here. I'm going to combine this with this. Okay. And so this is still going to be 1 minus J2. And now this is going to be the combination of 6 minus J2 in parallel with J5. Just going to leave it like that. And again, this becomes 12 plus J16 over, I'm just copying this from the previous step. Okay, so that's the value of the current source here. And so now I finally have a form that I can use to explicitly solve for I naught. Okay, I'm interested in the current going through this branch. And so now I can finally use current division to solve for I naught is going to be equal to 12 plus J16 over 6 minus J2 times, so in the numerator is going to be 6 minus J2 in parallel to J5. This has to be over. So actually, let me, it's going to be hard for you to see. Let me try it again. first of all, I'll write, oh, another visitor. Okay, so this is my current. This is impedance 1, and this is impedance 2. I'm interested in determining this current. And so what I'm going to do is say I naught is going to be equal to 12 plus J 16 over 6 so I had to let in another student. 6 minus J2 multiplied, and I'm just going to call this, I'm going to call this Z combined. Z combined over Z combined plus 1 minus J2. And I have that Z combined is equal to 6 minus J2 in parallel with J5. Finally, when you carry out all this arithmetic, you end up with I naught is equal to 3.9 angle 99.46. Only other thing I just want to clarify here is if anyone's not clear as to what this notation means, what this means is 6 minus J2 times J5 divided by 6 minus J2 plus J5. And so in this case, it would be equal to be 10 plus J30 divided by 6 plus J3. So that becomes this. And then you plug that into here. And again, if you have a calculator, you can just evaluate this complex multiplication. And so this is the phasor corresponding to the current flowing through this branch of the circuit here. Okay, we're going to move on, try to get through as many of these as possible. Okay, this is the important one because this is, you're definitely going to see one of these on next Monday. And so Thevenin and Norton analysis. Remember the steps. There's two things you got to solve for. You got to solve for the equivalent impedance when viewed from two terminals in the circuit. So looking into the circuit, you'll disconnect your independent source and you'll add up all the impedance that's in there. That's the Thevenin impedance or the Norton impedance. And then there's also the Thevenin voltage, which is just the open circuit voltage across terminals A and B. Or for Norton analysis, it becomes the short circuit current between A and B. So there's two steps. Step number one is disconnect your independent sources and solve for ZTH. If there's a dependent source in the circuit, you don't disconnect that. Instead, you apply a test voltage across terminals A and B, and then you use Ohm's law. And then step two is to either solve for VOC in the case of Thevenin, or solve for the short circuit current between A and B in the case of Norton. And once you have two of the three properties, you can use Ohm's law to get the third. And so let us try to do one Thevenin, one Norton here in the class. We're not going to do the one that's in the lecture. We're going to start off with this problem, which is, I believe, pretty straightforward. Because there is no dependent source here. Okay, we are asked to find the Thevenin equivalent across terminals A and B. Okay, so the first thing that we're going to do is we are going to disconnect this source. Okay, so we're just going to disconnect. I don't want to do that. Let's see. Let's just. Okay. Okay. And we need to look how much impedance is viewed from terminals A and B. So I'm actually getting you guys to help me here. How much impedance do I see on the path from A to B?
Minus J4.
Minus J4. What about the other resistors? What do I have to consider these?
Wouldn't you have to? Yeah.
And so you have, let's see. You have this node, right? And then this node. So the capacitor is connected between those two nodes. And so is the combination of these two. And so, you know, it would be something like 6 plus J2 in series with negative J4 plus 10. Right, so to go from this point to this point, you have a parallel, you have two possible choices. You can either go through 6 plus J2 or minus J4. And then no matter what, to end up at B, you have to go through the 10 ohms. That one is in series. So that becomes, let's see, we can do the arithmetic here, negative J24 plus minus J squared times 4. Oh, right, forgot the brackets. So it becomes minus J24 plus 8 over minus, oh no, 6 plus 6 minus J2 plus 10. And then when you carry that out, you get that ZTH is equal to 12.4 minus J times 3.2. If there's anyone unclear as to why I put these two in parallel and why I put this one in series, please let me know now. It's important that you guys see that. Okay, so now, oh, we have a question. Okay, good. I love when people say they understand. Okay, let me erase now this. Okay. Oh, I didn't want to do that. Okay, leave it here, it's fine. So now I want to compute the voltage between A and B. So which, in this circuit here, here's a good test for you guys. which element in this circuit is parallel with terminals A and B?
The capacitor.
Yeah, excellent. It is the capacitor. Why? Because there's no current flowing here, right? And so this here is my VOC, right? So this here is, I'm just going to call it VAB. That's great. And so now, because of that, we could just use voltage division, which makes our job a lot easier here. Oop, I don't know, it's not letting, oh, because I'm typing with white ink. Okay, it just becomes VAB is equal to VOC is equal to VTH is equal to 30 angle 20 times what? What's going to be in the numerator here? Negative J4. And what's going to be in the denominator here?
6 plus J2 plus negative J4.
Awesome. That's exactly right. That's equal to 30 angle 20 times negative J4 over 6 minus J2. Okay, like that. And then again, I'm gonna spare you of the nitty gritty. I'll just say that VTH equals 18.97 angle negative 51.57. Okay, so ZTH, VTH. All right, so I am hoping to do 2 more problems before we.
Professor,
Yeah.
can you just explain the part where the Thevenin voltage is the same thing as the
Yeah.
capacitor's voltage?
Yeah, sure thing. So there's no, in this circuit, right? There's no current flowing here because there's not a complete path for the current to flow. Right, so there's no current here.
Yes.
So this terminal is just this terminal. And this terminal is just this terminal. They're electrically equivalent to each other. Right? It's just if you touch the wire here or here, it doesn't matter because there's no voltage drop across this 10 ohm resistor. Right? So the voltage,
makes sense.
okay, good.
Thank you.
You're welcome. Okay. We're gonna do one now. This is probably gonna be a 2-pager. Oh, PowerPoint. Give myself as much room as possible. Okay, we are asked to find the Thevenin equivalent across terminals A and B. So remember, there's two things we have to solve for. We have to solve for ZTH and then VTH. So to solve for ZTH, first of all, we disconnect independent sources. We cannot disconnect the dependent source, right? And so the circuit that we're going to have is going to look like this. And we are going to have to put a test source here. And this will be 8 plus J4. And this will be V naught is defined here. This is still just equal to 0.2 V naught. And the arrow is drawn here. And then this here is the combination of the capacitor and the resistor. So it becomes 4 minus J2. Okay, like that. That is the circuit that we need to solve for to get 1 amp test source. And the thing that we're interested in is, and I'm going to call this point here, the notation here can be a little bit hairy. This is going to be, I'm going to call this V test. So the ratio of V test to 1 is going to be our ZTH. Okay, so my question to you is, what technique can I use to solve for this V naught here?
Could you use a mesh?
I could, but I don't need to. But it's related to mesh. So I would draw this out more if I had time, but I don't. So I'm just going to do KCL at this node here. And I have basically 3 currents. I have this current flowing in, and then this current and this current. And they're all converging on that point, which means that they all have to equal to 0. Which means that, yeah, plus 1 is equal to 0. Right, so this V naught over A plus J4 is the current flowing here. 0.2 V naught is the current flowing here, and 1 is the current flowing here. And so I can isolate for V naught is equal to -1 divided by, let's see. How did I do it here? So -1, 0.2 plus 1 over 8 plus J4. It's a little bit ugly without being able to write the fractions in. And it's going to give you the answer is 3.24 minus J 0.54. So that's not the answer for the V test. That's just the answer for V naught. So now comes the other tricky part, which is how to relate V naught, which is the voltage across this load here, into the V test, which is over here. And so what I did is I basically defined, defined I naught as flowing, let's see. So let's call this I naught. And then I naught multiplied by the combined impedance, this and this. Right, so this is also I naught here because everything's in series. And this is ground. So the voltage rise from this point to this point is going to equal to V test. So V test is going to equal to I naught times 12 plus J2. And how did I get 12 plus J2? I just added up 4 minus J2 and 8 plus J4. Now, what is I naught? Well, I naught is just V naught over 8 plus J4. Someone's had enough already. Okay. And so V naught is defined over here. So when you carry out this arithmetic, you get that V test is equal to 4.47 angle negative 7.6 degrees. So again, I'm just going to retrace my steps here. The first thing I did was I applied KCL at this node. And that gave me a solution for V naught, big V naught. I then figured out what the current was across this load here, the 8 plus J4 load. And I call that I naught. And then I multiplied that I naught by these two impedances, which are in series, by the sum of these impedances. And that gave me the voltage at this point, because this is 0 volts. A voltage rise from here to here, and then another voltage rise from here to here. So all these solutions are going to be uploaded onto Blackboard. And so RTH is equal to VTH, basically. Because RTH is equal to V test over 1. Is equal to 4.47 angle negative 7.6 degrees. Okay, so that's half of the solution. The other half is for VTH. And so to get the solution for VTH, we need to include the independent source back in. So I'm going to draw the whole circuit again. It's going to be the top node here. This is going to be the current source, which is now back in play. This is the dependent current source. Oh, I should have drawn that. The diamond. Okay, and we are looking for the voltage here between A and B, between A and B. This is my VTH. Okay. And I'm just going to fill in again the impedances, 4 minus J2, 8 plus J4. This is 5. This is 0.5 B naught. Okay. So here, the best thing to do is to do a mesh analysis. So I'm going to draw my two nodes here. Sorry, nodal analysis. If I said mesh. So this is node 1, and this is node 2. So I'm going to call this V1. I'm going to call this V2. And I'm going to just draw the directions of my current arrows. So I'm going to draw the current going down here, obviously this way, up here, down here. And so KCL at node 1 first. We have V1, V1 minus V2 over 8 plus J4. That's the current flowing here. Plus 5, that's the current flowing here. Plus V1 over 4 minus J2 is equal to 0. That's my equation number 1. KCL at node 2 also has 3 currents. And we have 5 plus V1 minus V2 over 8 plus J4 plus 0.2 V naught is equal to 0. But notice that V naught is just defined across the current source. V naught is just equal to V1 minus V2. Therefore, we have 5 plus V1 minus V2 over 8 plus J4 plus 0.2 V1 minus V2 is equal to 0. So that becomes our KCL equation at node number 2. And so the matrix here, which I'm going to try to draw, I'm going to draw it. Let's try to draw it over here. So this is just a two-dimensional system of equations. And two variables are V1 and V2. So when you evaluate this expression, you get currents of, this may not fit actually, but I'm going to do my best. Yeah, this is not going to fit. Just see if I can move this out of the way. Second. So the first equation is over here, and the coefficient on the V1 is 8 plus J4 inverted plus 4 minus J2 inverted. So it was a sum of fractions, basically. Not having a good time here. And the second coefficient is just minus 8 plus J4, negative 1. Put that over here. This coefficient becomes 8 plus J4 inverted plus 0.2. And this coefficient becomes negative 1 minus 0.2. Okay. And so that's our mixing matrix. That's our linear system. And then again, go ahead.
Oh, that minus 0.2, that's not in the exponent, right?
No, it's not. I'm sorry. Yeah, that's just you'll have it again in the note. But yeah, this is just minus 8 plus J4 to the power inverted, and then a separate term minus 0.2. V1, V2, and this becomes negative 5. Both the coefficients here are negative 5. Okay. And then when you solve this matrix, and again on the exam, we do not ask you to actually solve the matrix. We just ask you to arrive at the matrix equation. It becomes 7.35 angle, 72.9 degrees. It's a quick remark here. In doing this, it's very easy to make a arithmetic mistake. And so there's a strategy in doing these on the exam, and that is to not evaluate anything until the very last step. So it is okay to write it like I've written it here and here. And it's actually helpful for me because I can see what you're trying to write. And so I am perfectly okay if you do not simplify your complex numbers until the very end. And then if you make a mistake in evaluation, I can still give you a lot of partial points. Okay. So you will probably receive one more. We had one more problem that I wanted to cover today. That was Norton's theorem. I'll make a video covering that. And the section on op-amp circuits, I don't think there's really nothing conceptually novel there. It's just the application of the input-output equation of an op-amp, but with complex numbers. So there's nothing really critical in terms of conceptual items that we use in the course. But I will make a video to kind of demonstrate, to tell you how to solve this problem, because it is a good practice for your exam. I'm gonna let the TAs do the last lab. Just some reminders before I sign off. Please take the time to fill out the course survey. Please do practice on some of the problems that I've posted from chapters 9 and 10 in the textbook. And please remember to upload your photo ID before next Monday. Okay, and I'm gonna let Sam or Tariq, I'll lead the labs now. Thank you guys for sticking it through the semester. I had fun teaching you guys, and I look forward to seeing everybody on the final exam with what I hope will be a fair and fairly relaxing end to your semester. I won't stop the recording, but I will leave it. And I'm gonna make Sam the host here. Make host, yes. And I'm gonna, won't let me make you a co-host, Tariq, but next time. Bye-bye.
Okay, good afternoon. I hope you enjoyed the lecture. It was too much even for me, actually. So for today's lab, I don't think that I will cover anything new for for the lab module. I wanted to cover more, but that would be too much for you guys because you are going to have the final exam next week. So I will reserve this session for any other question you have, because tomorrow my office hour will be delayed, or I will not hold it at all, depend on how I feel. Yes, so sorry about that. So if you have any question, feel free to ask me. This is well, I will still answer your question if you ask me on Slack or over email, but if you have any question, we can solve it together along with your classmates. So go ahead. So I will share my screen first. And I think this is my screen, and one of the let me check to make sure that I have the chat ready first. Okay, move it over here. So one thing I want to clarify, I think not two people asked me before class on Slack on how do we connect this type of circuit. So what I am going to do now is I'm going to do this. 1 second. I will open this thing. And I'll move this one over here. And I will move this one over here. it smaller a little bit. This one a little bit bigger. Oops. Come on, get bigger. Yes. So I will cover this one first. Feel free to interrupt me if you have any question. So for this one, like to connect any circuit is actually really simple. You just need to follow this exact schematic to connect the component. For example, for this guy over here, what we are having is like the power supply connect to the non-inverting terminal of the op amp, and then we have two resistor, the R1 and the RF going into the inverting terminal, and both of them share one single node over here. And together like that, like the op amp will connect to the ground and the output will connect to the oscilloscope. So on the schematic, one second. Let me remember balance, inverting, non-inverting. Okay. So what we 1 second. Move. Come on. Come on, my tablet is not moving. Okay, it's working. So what we are having over here is this guy 1, 2, 3, 4, 5, 6, 7, 8, and this one is number 2 is non-inverting, inverting. So like just draws again 1, 2, 3, 4, 5, 6, 7, 8. So this like the power supply come into the non-inverting terminal. So it will come into pin 4, pin number 3. I mean, this one will be the power supply, and then we connect one to ground, and then we have the inverting terminal connect to R1, RF, and they share the same node. So and then R1 also connect to ground. So what we will have is this type. This one will be R1, and one terminal we share the same node with the circuit, and then we have the RF. This one is RF, and like as you can see, they share the same node, and it will connect into the inverting terminal of the op amp. And then what do we have next? We have next is the RF, like this one is RF, sorry. RF will connect to the output terminal. What is the output terminal? I don't remember, which is pin number 6. Wait, it's the other way around. Oh, okay, my bad again. Yeah. 5, 6, 7, 8. 5, 6, 7, 8. And number 6 is the output. So we will connect this guy to this guy. And then this one to the oscilloscope. And yeah. And then we have, yeah, that's all. So this is basically the whole schematic, and then we will connect this guy to the oscilloscope, and remember to pay attention to this guy over here to make sure that you are grounded. And then the next thing is we need to power up the op amp, which is the pin number 4 and pin number 8, like pin number 4 and pin number 7 from the schematic. So what we will do is we will connect this guy to the positive side of the 12-volt power supply over here. It will be 12 volt, and then pin number 7 to negative 12 volt. And that's how you connect this one to the non-inverting amplifier. Any question? Oh, yeah, the number is different. I just realized that, sorry. So now you only have to translate this one into the breadboard, and you should be able to do that right now. If not, you are in big trouble.
Sam, I have a question.
Go ahead.
Can you zoom back in?
Zoom back in.
So from the wave, we're gonna plug in into 3, and also the ground to 3.
Ground to 3. What do you mean by ground to 3?
No, I mean the wave, the wave, uh,
The wave
generator.
Yeah,
Yes,
yeah.
we're gonna
Like
plug
like
both ends into 3.
No. In like this one, that they don't go into 3. You have to connect the like one side over here to the wave generator. So what is basically is this is the correct represent. Oops. Like this. So this one is will go to the positive side of the wave generator, and then this one will go to the negative side of the wave generator, and this one is the ground part as well. And so technically, like they kind of share the same node over here. Did I answer your question?
I mean, like in the picture, it's showing that the V initial is grounded also.
The the V initial, like the VI, you mean?
Yeah.
It's grounded. That's why we connect the like. That's why we connect it to the like the ground part over here in the wave generator. Can you see the movement? Like this one already act as a ground, so you don't have to worry about that. Because the idea of the voltage source is provide a potential compared to ground. So like this, like the yellow wire is already providing the potential relative to the ground pin that next to it. So all we need to use, or what we can do is we can use it at a ground pin and use it to share it with the RL and the oscilloscope.
So the ground is only sharing the R1 and the oscilloscope, the negative part of the oscilloscope.
Yeah, like the ground, like that's why this image over here, the ground part is connected to here. Like if you look at my image, yeah, like the ground part go all the way from here to here, and then you have the oscilloscope connect to here, and this one will act as the ground for the entire circuit. Like we can see, like like this one was for the inverting amplifier, and like we have the non-inverting terminal connected to ground. So that's like the wave generator ground act as a ground for the entire circuit, which do like if would be normal. And the same thing for
Okay, thank you.
Yeah, so like it's very simple. You have to like as long as you understand that whatever, like if we need a potential, then we need to like when we are saying like there's a potential, then we need to have the reference point, and the reference point is as long as like it stay consistent across the entire circuit, then we are good to go. So like to demonstrate that, like I don't have the demo ready, but what you can do as well is you can connect this guy to we can use this pin as ground as well, and like there will be no problem to it. We can connect one pin of the ground of the wave generator into here, and another pin, another jumper wire into this one, and it would act as the same thing. So like as long as like the circuit is ground to the same node, then we're good to go.
Uh, Are you gonna add anything to module 2, or we're not adding anything?
I'm good with that. Like, I think like with all the questions you guys having, I think you already have enough on your plate for the final exam and for the final lab report. So yeah,
I have a question for module 0.
module 0. Okay, go ahead.
Do we need for the regular circuit, the DC circuit, do we need still?
Well, yeah, I think you need to use the regular circuit for this. Well, it's up to you actually. I don't care how you power your circuit as long as your LED light is stable. Then I'm good with that. Like I said, like during like the module 0, what you can do is you can actually connect this guy all the way to the wave generator over here, and then set the waveform to DC and do the offset like we did for the palm, and it would still produce the same result. So I'm good with that actually.
Okay. And do we need still to put a picture or a video for the stable light?
That's a good idea. I think well, I think for the blinker, like I only need that for the blinking. So like for this guy, you can just take a picture. I can see like from your image, like your LED light is not blinking as long as light up and your circuit is connected correctly. I'm good with that.
Okay. And do we need a picture of the oscilloscope for this one? Because when
Yeah,
we're doing it
yeah.
together,
Yeah, I think like I said that in the lab report. I didn't. Well, okay. I will need to add that. I think I think I said that like in the submission part, but like apparently I forgot.
no, I
Well,
think it's up. It's up.
oh yeah,
Because
like over
that's
here, like I said, like in the report, fill in the table, and then a screenshot shot of like the wave generator, which is blah blah blah, and the oscilloscope as well. So yeah, I said that.
even for the DC.
For the DC, yeah, like if you use DC, then just show me. If you are not using DC for the stable LED, then you don't have to. Just use common sense.
I used the regular method. I didn't use the wave generator. I used
Okay,
just the bifolds.
yeah, like idea is like if you're using like the blinking circuit, then like just the idea was just to show me how you guys are generating the signal. Like if you're using the like the onboard power supply, then you don't have to. But if you're like if I saw you connect to the waveform generator and the LED light is not blinking, then I think okay, maybe you use DC circuit, the DC offset from the wave generator, then like I think you might need to attach a picture to that and show me that like okay, you really got that. Yeah.
Okay.
How
Thank
do
you,
we
Sam.
calculate the how do we calculate the ideal gains again? You have to go back to your slide. Like it depends on the type of circuit. If like if it's an inverting circuit, then it's I think IF over IL times the V0. If it's non-inverting circuit, then 1 plus IF over IL times V0. And then for the different, the formula is there. You have to look at for yourself. Like the ideal gain is you don't have to do anything experimental. All you have to do is like how you did for the homework. And this one is the basic of basic in like the non-inverted, in calculating the gain for the non-inverting and the inverting and the difference. And yeah, like that part is for analytical. And then like for the actual gain is what you need to have the circuit, you need to like assemble it and need to use the oscilloscope to measure the V output versus the V input to calculate the actual gain. This can you again briefly describe the circuit you draw? Okay. This one you mean? So okay. For this one, so the idea is first I think that you know that like there's a dot, like if we like compared to the tiny op amp over here, there should be a dot in this position to tell me that this first pin is pin number 1, pin number 2, pin number 3, 4, and then from this one is 6, 7, 8. So like that should like I'm just making sure. And then the next thing is you will need to look at the exact schematic of what kind of circuit you want to assemble and analyze it. First, you look at we have the VI, the initial like the initial voltage source over here. We have the negative terminal of it connect to the ground. And then we have the positive of it connect to the non-inverting terminal of the op amp. So like, and then we look at the schematic over here. And we say, okay, the non-inverting is like terminal is number 3. And number 3 is 1, 2, 3 over here. So what we are doing is we are using the wave generator as the voltage source. So we will connect the positive terminal of the waveform over here, or use a jumper wire connect all the way to the non-inverting terminal on the op amp, which is pin number 3. And then we look at the circuit schematics again, and we say, okay, then the negative terminal of the voltage source is connected to the ground. So, and then this one acts as a ground already. So yeah, we don't have to worry about that. And it will be US ground. So all you have to do is connect this guy to the positive terminal of the wave generator. And next we have RL and RF. The RL, we can see one side of the RL is also connected to the ground. So we have to make sure that like that's why over here in the schematic, like the ground side of the wave generator connect all the way to here. And then one side of the RF will connect to this line. So that like that we ground the IL. And then we have like the other side of IL share the same node with RF as well as the non-inverting terminal. So that's why we have like the IF connect to the non-inverting terminal, which is number 2, the inverting terminal, which is number 2. And then we have the IF as well. So we need to connect it like the IF to the non-inverting. So all of them should share the same node. And we look at over here on the other side of the IF resistor, it's connect to the output of the op amp. So that's why like we will connect, like you can do like use a jumper wire or anything, connect the other side of the resistor in with the output, which is pin number 6 on the op amp, to make sure that they share the same node like this over here. And because we want to measure the voltage of the output, so we will connect one side of the oscilloscope to the terminal number 6 as well. So they all of these guys share the same node. And the other side of the V0 node that we're measuring connect to the ground of the like connect to the ground. That means like, and we're using the ground on the wave generator as our true ground. So all of them will share the same node like over here. This one is oscilloscope, and this guy connect to the, what is it called, the wave. And yeah, that's all I did. And then, oh yeah, I forgot. And then we need to power the circuit as well, because like this guy doesn't like, oh, we all assume that like when we look at the schematic, the only thing that I'm missing is the power supply to the circuit, and the actual image should be something like this. V plus and V minus, like this one is like on way there, but like for the simplicity of the schematic, people often ignore it, and we only look at this when we need to power the op amp. So we need to power the op amp, and that's why like there's some the saturation come in when you have the gain, like the multiplication of the gain time the voltage source is over the power supply, then it will be capped at the potential of the power supply. So to do that, we look at this, which is the pin number 4 and pin number 7. So that in that way, pin number 4 over here will connect to the negative side of the 12 volt. I don't remember which one is 12, which one plus, which one is minus. I would say this one is 12 and this one is plus. So yeah, like this one connect to one side, the negative side of the 12 volt, and like pin number 7 will connect to the positive terminal of the 12 volt voltage source. Like we are not connecting this guy to ground because otherwise will be like the V peak to peak will be plus 0 to plus 12 to 0 and not plus 12 to minus 12. So yeah, and that's why like when you do this experiment, like there will be a step where whenever you try to increase the ideal gain, your volt, like the output of the voltage will be capped at 12 volt. So like yeah, that's the idea of this experiment, to show you that like you can indeed read the level of like voltage saturation in real life. So yeah, any more question? I hope I answered your question. Let me try some other first. Do you guys want me to work over the different the what is it called, the different amplifiers as well? I think it will save you guys lots of time. So and then we still have some time. So if you don't want me to spoil like your hard work, then I will not do it. So okay. Oh come on, like I don't like spoiler, but okay, if you ask for this. So let me take a picture of this guy and then we can work on this guy. Yeah, like I said, like you guys should be able to look at the schematic and be able to translate the schematic of the circuit into what is it called, into a breadboard circuit. Otherwise, like Dr. Para and Dr. Bixson will put you bad way for not be able to do that. So if we are good with this, I will try to eliminate this guy. I will erase this guy. Eliminate is a bad word. Yep. Let me make bigger, baby. I would not use this like the breadboard as the thing, but like I will tell you generally how you should connect to it, but not like spoon fitting and make any like doing any major spoiler to that. And let's see, we will need to look at this guy. So to look at this guy, so for this guy, we have two types of voltage source, and all of them share the ground. So that's good to know. As well as four, like R4 also share with the ground. And then we have the V output also ground, that's obvious. And then we have R3 and R4 share the same node into the non-inverting terminal. And we have R1 and R2 share the same node going to the inverting terminal. So that's the idea. And let's do it. How do we know it's ground node? Well, it's connected to ground, so it's ground node. Yeah, like we have the positive side connect to the ground also, like all these not like this whole node over here is the ground node. No, in the breadboard. So the idea was you will like we have the ground over here. We will use both of these guy, and then they like we have this like the symbol here. This symbol is the ground, and as long as they share the same node, then they are ground. So what I will do is I will like already connect one guy to this, I will get another jumper wire and connect this guy to this position as well. So now of this is the ground node. And yeah, as long as like all these share the same node, then they are ground. All the ground node from the voltage source share the same node along with the ground node of the oscilloscope, then they are ground. Like the ground is all like depend, like the ground is just the like what is it called? It just depend on your reference. So for example, if you put the ground node like in somewhere with 1 volt, then your voltage will be like 13 volt. It will vary from 1 to like 13 instead of 12 to 0. So the ground node is just depend on like whatever it just there's no voltage there, so just 0. Yeah, so hope I answer that question. Clean this guy up, and we will draw the
We use
hello, yeah, go
yes,
ahead.
we use both wave generate channels for wave generators in this one, right?
Like it's a little bit difficult to hear you. Can you repeat that again, please? Thank you.
I'm saying, do we use both wave generators channels?
Well, I think I fixed one of them as either 5 volt or 1 volt. I don't remember. And like it's I think let me take a look. Well, experiment 2, 3. I think I fixed one of them at 5 volt. So you have 2 options. You can either connect this guy, the W2, the wave 2, to a wave generator, or you can connect this guy to the onboard voltage source. Like, okay, then in that case, it work just as well. And in the like, it's also mean like, for example, you can connect another jumper wire, 5 volt. Then we like it's a little like okay, because we only have 2 groove over here. This image only show 2 groove. Let me find another one of mine that says 3. Okay, this guy has 3. So I will use this guy. So like assuming we don't have this wire, and because like we already use this wire to power the supply. So that's let me see. Okay, we have the 12 volt. Okay, let's do this. Let me go back to my image. Blah, blah, blah. So like this image is a little bit difficult, but okay, this will do. Okay. So let's do it. Like I will try to do it, and then you can stop me anytime. Like you can use the 5 volt, but it's a little bit difficult to like to speak into work. So I will try to demo it using my drawing, and then you can ask me my question if it's not clear. So we have 1, 2, 3, 4, 5, 6, 7, 8. And this guy is the op amp. And what we know is we will again ignore pin number 1 and pin number 5. And then we look at the inverting terminal first. For the inverting terminal, we have R1 and R2. So we will connect the similarly. This one is annoying. Okay, 1 second. Yeah. 1, 2, 3, 4, 5, 6, 7, 8. So we have R2, R1 and R2 share the inverting terminal. So we have this guy come over here. This one should be R1. And then this R2 go to the output terminal, which is pin number 6. So what I will do is I will connect this guy like this all the way to pin number 6. Okay, so this one should be R2. And pin number 6 will also connect to the oscilloscope as well, OS plus side. And then from this image, we can see that the other side of the R1 is connect to the V1. So this one will connect to the one positive like one side of voltage source. And then we have R3 and R4 connect to the non-inverting terminal. So what we have is R4 is okay. So this one is what we will have connect to this guy, and this one will be R3. And this one is exactly following the I'm using the schematic as a base, and then you can move the component around as long as all the connection are maintained correctly, then you should be good to go. But I'm doing exactly what I would do if I look at the new schematic as well. So we have R3 and we have R4, and this R4 is connect to ground, so I will leave it for now. And this one will be V1, and R3 will be connected to the positive side of V2. And then we have the negative side, and and then we need to power this guy also. So this one will be go to V minus, and this one go to V plus. So we are good to go. And this one will connect to V2 will be 5 volt, and this one will be go to wave generator. And that should be all. And then all the so what we have next is we have the negative side of wave chain, and then we have the negative side of the GND of the ground. Yeah, I'm assuming that you are using the onboard ground of the 5 volt. And then we will show this one is one single line I'm representing for the and we will connect this guy to this line and this guy to this line. And let me check. So we have 3 ground, and we have another so we have the ground for the 5 volt, and we have the ground for wave generator, all connect to the same ground. And then we have the we also need to connect the ground of the oscilloscope. So this one is the ground for the oscilloscope. Oscilloscope. And yeah, this one should be the ground line, the GND line. And yep. So this is how you should connect your different amplifier circuit. Any question for me? I'm just yeah. Okay.
What was WG again?
WG is wave generator.
And that's basically the ground also.
Wait, what? No, this one connect this WG over here.
No, I mean the WG negative.
Oh, okay, yeah. You can bundle them together and make all the ground bundle them together, and they should be fine.
Okay, thank you.
Yeah. Oh boys, if I have one more session with you guys, I will use this part over here, this component. Yeah. The longer op amp you guys have in your circuit kit. Yeah. This guy had 3 small op amp inside. It's really cool. So maybe after you guys finish your final exam, if you want, I think I can cover the GitHub session as I promised at the beginning of the semester, as well as we can go over some fun circuit, why you have the circuit kit. Like we have a lot of fun component inside the kit. So if you are really interested in that, we can go over some circuit. Okay.
Yeah, I see that there are a lot of components that we don't use. We only use
I think
resistors, LED lights, and
like
op amps.
some component will be used for your next class with Dr. Para and Dr. Bixon, because I can see there's some thermistor in there. So potentiometer. Yeah, that one, like for me, it's not that fun to do the potentiometer. Like I did some circuit with that, but it's kind of boring because I mostly work with sensors. So like I have more experience with sensor than with potentiometer.
Be excited to
Because
know that you'll be building an EKG next semester.
Yeah, actually,
Is it EKG?
well, the EKG is very simple. Or you like the idea was I'm not sure if you have like the pin out in this. You don't have the pin out in this guy, but I think this component I'm not sure. I'm not really familiar with like how you do the programming with the programming with this board. But the idea of the EKG was that like it's completely the same thing. So what you need to do for the EKG is like for whatever you are measuring, the EKG is basically for whatever sensor you are having. Like the sensor will have the value vary from either from 0 to maximum at either 3.3 or at 3 volt or at 5 volt, and out of like those like along like anywhere in between. For example, you have 1 volt, so that means like there's some EKG value associated with 1 volt, and it's on like there's other value like for example 1.2. It also depend on the resolution of the sensor as well and how sensitive it is. And yeah, so the idea was like you read the voltage of the sensor and translate that into you will use the what is it called, the info sheet, to like translate those voltage value into the actual reading. So don't worry about that too much, because before you work, like you will work on the EKG, you will have to work on the thermistor first. So it's the toned down version of like the EKG. So you will have like the thermistor, it will measure the voltage, like the temperature in the environment or in the water, and then it will return a voltage value for you guys. And the idea was like you will read that voltage value and translate, use the info sheet to translate those value in the voltage into Celsius or Fahrenheit or Kelvin. It depends on like the type of thermistor you are using. Yeah.
Okay. This is just for your future reference. When you do take Bixen's class and that thermistor test, make sure you have a backup, because there is a chance that the thing will break in the middle of the test and they will fail you. So just have a backup just in case.
Yeah.
Backup of what, Tariq?
What's up?
A backup of what?
For the thermistor.
Yeah, the thermistor. So like you'll have your main thermistor that you're gonna test during the examination, but like leading up to the test, there may be a case that the circuit breaks. So just have one that's like you have a backup. You'll usually work in teams, by the way. You won't be doing these tests alone.
That's 405.
Yes.
So that's next semester. Cool.
One is the thermistor. Is my camera is, oh boy, my
Oh yeah.
my blurry is not working. Okay.
Do we keep the circuit for next semester?
That's a good logistic question that we decide not to look into until the end. You guys finish your final exam. So yeah, that's another logistic nightmare. So yeah, it's depend on the school. How do we connect to the 5 volt? Do you use jumper wire? Like we have like the image over here. Oops. Yeah, like one is the board and you have the 5 volt and you have the ground. So what you will do is you will connect this guy actually to all the way to the ground. And then like this ground over here will share the same line with this guy. Yeah, so it's really simple. Like for the sensor, as long as you understand the principle, I think Vixen will cover that in class for you guys. As long as you understand the principle, then the idea of not like the hard parts were not like how you assemble just like your circuit, but the hard part was to like stabilize your reading, because there will be a lot of noise and therefore there will be a lot of fluctuation as well. For example, if you do the EKG and like there's some hair and in the position like on the skin part where you are attaching the probe, and like it will affect your reading. So like you have to either do the analog filter or a digital filter to filter out the reading. So yeah, getting it's the principle of like 80 and 20. So you like for the 80% part, it's like you will only spend 20% of your time, and then the last 20% will consume the 80% of your time. Ugh. That's all I have to say. There's 45 minutes left. There will be no what is it called, the office hour tomorrow. So if you still have any question regarding the circuit, this is your last change.
And one last thing, we only do modules 0, 1, and 2, right?
I think you forgot you have to buy the circuit and did this one as well. So yeah. I'm kidding. Yes, like model 0, 1, and 2 only. Like we are out of time for more like model 2 and 2 plus and module 3, which is about AC circuit.
Okay, and you want those in different PDFs, right?
Yeah, I think I will upload those PDF into like Blackboard, but like because Dr. Domotowski gave me those PDF like for when we use a different type of circuit kit. That's why like I need to translate like how you assemble the circuit using from the old one into this one. That's why it took me a lot of time to write this thing. So yeah. We don't have the programming capability. This guy, I want to show you something. Okay, try it and let me know. I will just stay here, like okay, until everybody leave. If you have any question, feel free to speak up. Stop sharing. You are very much welcome.
Sam,
Yes.
just wanted to ask if I'm having trouble with the circuit later on. Like, I don't have any questions right now, but I still didn't finish the whole thing. Can I send to you on?
Yeah, on Slack. Like I have helped a lot of people on Slack, so go ahead and do it. I'm fine with that.
Okay, because I know that you have a lot going on, so I just
Yeah, like I will take a bit of time. Like it depends on like where what I'm doing at the time. If like I'm just reading some paper, then I can help you. But if I'm writing something that like it will take a bit of time.
okay.
So yeah.
Yeah, I understand that.
So just like for sure, I would say it's May 25th, right? The deadline, the last day to submit is whatever.
Hopefully.
Yeah, the May 25th, and just like any time between like before the deadline, I'm good with that. Like and then I think I should be finished on the 24th. So like after that should be fine. I can like have another session on Sunday, on Tuesday morning. Where do we add the oscilloscope for different amplifier? Like it's the same thing. Like it's the same thing for the different. Like the only thing we are made like the oscilloscope should the position of the oscilloscope probe shouldn't change for all the three circuits. Like they all mean the same thing. So like we connect like the positive side of the oscilloscope to the output at pin number 6, and the negative side to whatever ground that you are having for your circuit. As long as they share the same ground, then that's good to go. Did I answer the question? That's good.
Good luck on your
Yes.
elementary. And
Thank you very much.
yeah, thank you for the semester.
Yes. Actually, I'm planning to hold some more like optional lecture if you want to. I just want to practice on my presentation to you guys. Haha.
We can do that. Friday will be good if you're doing a practice session. I think Friday morning will be good. But
Yeah, okay, yeah, like if nothing changed, maybe Friday the week after, like Friday next week should be fine. Like if I'm not decide to go on hiking, so yes, like I can do Friday.
or if it's after the exams, I don't know. Like you can ask on Slack, so like you get the role. But
Okay,
if you need help,
okay, yeah,
I don't. Have a good day.
you too. You are very welcome.
You're welcome.
What's up?
What's up?
I thought you were like about to say something. Okay.
No, I said you're welcome. Sam.
Yes.
So I got an email today
Mhm.
from the hospital for special surgery.
Okay. Oh, that's good. I think.
No. The funny part was that they were saying, "Hey, you applied to this position a while ago. We rejected you, but are you still interested in the position?"
And that is a strange way. Okay.
Mm-hmm. And
Right.
I have no idea what the position was.
Okay. So ask them, I guess.
Yep. I'm waiting for them to respond because I really don't remember what the position was about.
Okay. Maybe because like another candidate get declined the offer, so they bump you up, I guess.
I assume so.
Okay. We still have about 15 minutes.
Mhm.
Let's see if people have any questions. Still take 2 more. Oh boy. Oh boy, I hope that the para remember me. Like I took I took the class with him last semester. So, yeah.
I mean, I'm sure you'll say good things. I hope. I have 2 more people to get the reference survey done.
Okay.
Yasik said he's a little bit busy the next 2 days.
Hmm.
So he's gonna try to finish it by Wednesday, I think,
Okay.
if not Thursday. And then there's Andrea. But I'm gonna wait an extra day to see. Cardoso finished today.
Okay. Yeah, I think I just finished class and asked her to do the survey. So yeah.
I'm ready to do my 3 to 11 p.m. shifts. Oop, we have a question.
For experiment 3 table V1 V2 value, we will change in the offset exactly. Experiment. Let me check again just to be sure. Experiment 3. I don't remember the experiment 3. Ooh. Well, like I said before, for V2, you have the option to use the 5-volt voltage source on board. So you don't have to like it's not necessary to use two-wave generator for experiment 3. But for V1, you definitely need to connect it to the wave generator and use DC offset. Yep. Did I answer the question? Yes. Okay. Yeah. Okay, now I have no new offer for interview. So now I just waiting times. Let's see. I got like 4 or 5 interview and 3, 4 were good, but yeah.
On my interview with MSK was pretty good. I'm so proud of that one.
Okay, that's good. Like for which position?
That was for it's the one that acts for the 5 references.
Okay.
It was for
Which position?
support technician. Yeah.
Okay.
Yeah, I would be working in the surgical rooms.
Oh boy, surgical room.
I'd
Oh.
be maintaining those medical devices.
Oh, okay. So after doing the surgery, yeah,
Mhm.
I guess. I hope.
Before surgeries, the preventative maintenance.
Mhm.
Usually my job is to double check to make sure that they're working properly, and if not, to contact the manufacturers on how to diagnose. Yeah.
That's how fun. Okay.
The fun part, I don't know if you heard earlier, 3 p.m. to 11 p.m.
That's not fun. That's not fun at all. I think in the past I know, and I don't know how to say the word anesthesiologist, like the person who put the patient to sleep.
Oh, the anesthesiologist.
Oh, anesthesiologist. Okay, that's
Anesthesiologist. Yeah.
that shift is from 11 p.m. to 7 a.m.
Yeah. I mean, they're actually like one of the easiest jobs in the surgical room, because they just have to maintain the anesthesia levels so the patient doesn't wake up.
Okay, but like if you do too much, the patient die. If you do too little, the patient is in trauma. So yeah, like
That is true, but a lot of their job is just maintaining the medical device that's doing. So technically, we would be in trouble.
okay.
Ooh.
Yeah, so the surgical room, okay, that sounds very cool, very fun. Maybe like after you got in, you can like have me as like a guest, like you can refer me to do an intern over there for like 3 months to learn about the surgical room, I guess.
Yep. Some of the devices that I would be working with would be the, what was it called again? The
like
endoscopic like microscope, I think it's called.
yeah, I know that things.
That's one of the devices they like gave as an example as to what I would be working on.
Okay, that is really fun.
I think one of the main things that they were looking for during that interview was that am I trainable? I think that was one of the things they were looking out for. Now that I reflect upon what they were asking me.
Oh yeah, that's true, because like you don't know how to operate medical device out of school for sure.
It's like I'm sure that because we are researchers,
Yeah.
we have that advantage. Is like these we know how training is.
Yeah.
We can pick up on things pretty quickly.
Oh boy.
And won't get bored with like monotonous work. Well, at least I don't get bored with monotonous stuff.
Oh boy, the guy I had interview with this morning worked closely with Dr. Para. He like his boss like meet with Dr. Para every week actually. So yeah. Like when he talked about like he was doing the experiment where like you have the functional MRI, and like they will show the subject a video and like looked at like how the brain function during like the video showing. Now look at like how that yeah, that Dr. Parra is doing. So and then
It's
he
like I gotta double check here. It's like I gotta double check with my insider.
Oh yeah. And that was like the only lecture that I did like Dr. Para asked us to like attend for like a long time, like a long times ago. And for example, like for some reason it's stuck inside my mind, and now it just came up randomly. So yeah. Oh boy. And the other position was at Hopkins University. So
Where's Hawking?
At John Hopkins.
Oh, John Hopkins.
Yeah.
I heard Hawkins. Was like,
Oh. Yeah, like I think like that position will ask me to do exactly what like I think Brian is doing right now, like the coordinate research within the group, the researching group in the department, as well as doing the analysis of the motion data, which is what I was doing before. So yeah, it's pretty fun. But like start in June. So like she mentioned that like if like all like there's a better candidate that can start in June, then like she would like not selected me.
what? Why would she tell you that?
Well, just to be like upfront and be clear about that. I don't know.
Like, hey, I just want you to know. If we get someone in June, nothing for
Then
you.
yeah, like even if I want to start in June, like I cannot because like I don't have the work authorization until at least August. Yeah, like late July, early August. Like she can train me, but I will not get paid. So yeah, I don't know. Okay, I think Koban, do you have any question for us? I think like we can leave right now. I'm not sure if he's still there. Oh boy, I have to write the report for Dr. Cardoso as well as the plan proposal for his class, and that's totally.
How much left do you have of the report for Cardozo?
I haven't started a single work actually.
How long is this paper supposed to be?
I don't know. Like I have the he basically asked me to write how the code work, and I already know inside out how everything works, and I already have like all the basic information like ready. I already wrote the majority of that like of how the code work, but it's not just in the formal format of a research project. That's why.
Okay.
Yeah.
Just making sure, because
Yeah.
given my experience,
Hmm?
I would be a little traumatized.
Like in my code, I think like I wrote all the documentation and I know exactly how my code work. So like if I have to write everything, that is will probably take me one day at most to write all the protocol of how the code work. So yeah.
Okay.
Yeah, and that will be about 10 pages, I would say. Like it depends on how detailed you want me to, but it's probably about 5 to 10 pages. Not that many. It's really it's the final product. It's not like I don't think it's the entire process like you did for your research thesis. You know what I mean?
Yep.
Yeah.
Oh, thank God.
Like if it's like everything is in the code base, so like I'm just explaining to you like for the record keeping purposes that how the code work, and in the future like you don't have to understand every single line of code to like know how the code work, how the program work. Yeah, so I think I will try to finish like the proposal for the ultrasound class today, tomorrow at the latest, and then I will start working on the report because like I got really good data. So I want to work on meet with him first to like go over, like make sure that everything is good.
That's good.
And then like we will start what is it called? The writing process. It would take me like he said like you can do it due by next Monday or Tuesday. So like over the weekend should be more than enough for me. I hope. Because Analisa asked me to write like last year, I guess, when we were in lockdown because like we don't have access to the lab.
Yep. Well, the last student has left.
Okay. I think that's it for us for this semester. If you want to attend my lecture next Friday, or whatever the time I
I
decide.
mean, yeah, I can come in and listen.
Yeah, it's
It's gonna be MATLAB, right?
well, like I need to decide because what Dr. Cardoso is in, like Dr. Cardoso is also planning to, so I need to check his schedule with. But the idea was to how to use GitHub to collaborate in coding with other people,
Mhm.
and how to because the idea of using Git was like, for example, you make like you have a working version of your code, right? And then you want to do some upgrade to it, and by doing upgrade you need to break this part, modify the other part, and then add a new part to it, and you are not sure if this part code is going to work. So like it's like the process will help you to make another copy of that one, and you still like at the same time you still have the working version of your code on the cloud, and you can modify, like you can play with the new, like the copy version of it anytime you want. And then at the end of the day, if it's your code work, then like the software will automatically merge the two parts together, like by doing the comparison to see what changed and what not, and this will like do the bookkeeping everything for you. And then if you decide, okay, this one is not going to work, I will scrap it out, and you just can just delete that copy, and you still have the working copy of like the working version of your code without like doing anything major to that. So yeah. That's a pretty helpful process to know. Like I don't expect people to know how to use it fluently. I don't know how to, but like the idea was like to have something to keep in mind, and like if like there's an opportunity or there's a need to do it, then you know how to utilize the tool because everybody is using it. So I think we should I should have stopped recording. Everybody will listen to our conversation.
It's okay. I don't know if they always reach the end of the.
Okay, I think we should leave. Like this is slide up the chat.
All right. I'll see you later, Sam.
Bye.